right, hey y'all, it's Mr. Kyle Myers, Mathematics. Jump into it. We are doing number 56. Newton's method seeks to approximate a solution f of x equals 0 that starts with an initial approximation x sub 0 and successfully defines a sequence x sub n plus 1 equals x sub n minus f of x sub n over f prime x sub n for the given choice of f and x sub 0 or x naught. Write out the formula for x sub n plus 1. If the sequence appears to converge, give an exact formula for the solution x, then identify the limit x accurate to 4 decimal places and smallest n such that x sub n agrees with x up to 4 decimal places. Okay, that's quite the mouthful. So let's jump in. It was actually really helpful. I did 55 before I did this one. And it was actually helpful looking at the answer key because it's a little confusing exactly what they want. So it was nice looking at it. I confirmed that at least the answer key, doesn't ask for the explicit formula. It kind of sounds like that might be what they want because they say give an exact formula for the solution x, but that's not what they're looking for, at least not in the answer key. If your professor is asking that of you, let me know in the comments now because it might take a while for me to get that follow-up video to you. I'm not going to be getting the explicit formula in this video. In fact, I wouldn't even show like in real time how to do something like that because it would take me a while. It would be a long video getting the explicit formula for this. So with that in mind, let's jump into this. I'm going to start with something that's actually not part of the solution. I'm going to start over here. And I like to start by plugging in f of x equals 0. So we just know what we're trying to get. And actually, the answer key had this. So I say that it's not part of the answer, but it actually kind of is. So if we set f of x equal to 0, 0 equals e to the x minus 2. So I'd add 2 to both sides. And I have this. And then if I take the ln of both sides, or I could do the change of base. One way to remember how to solve exponential or logarithmic equations is with this phrase. And I've probably got this in other videos, but just so that you have it, in case you haven't seen the other videos where I was talking about this, this is how I remember to change the base. The base stays the base. The base stays the base, and the others switch place. I'm going to try to squeeze that in there. So the base stays the base, and the others switch place. Something caught my tongue. So what does that mean? E is the base of the exponential expression, e to the x power. So that base would become the base of the logarithm. So if I'm switching from exponential to logarithmic, the base of the exponent e becomes the base of the logarithm e. The others are the 2 and the x, and they would switch places, meaning the 2 is what it's equal to, and the x is directly above and to the right of the base e. So those quantities are going to switch places. So instead of x being above and to the right of that base e, now 2 is going to be above and to the right of that base e. And then instead of it equaling 2, it's going to equal x. All right, you see how I did that? So hopefully that's helpful. It's a little bit faster than taking the ln of both sides. Not that much faster, but hey, every second counts if you're on a timed test. So if I took the ln of both sides, I get the same thing. Ln of 2 equals ln of e to the x, then the ln and the e would cancel, and I'd have ln of 2 equal to e to the x. Okie dokie. So the ln of 2 is equal to x. And what is that approximately? I want to write this out so that it is accurate to at least a few decimal places. So that way, when I get to the later part, agrees with x up to 4 decimal places, that last phrase, I will know when I've accomplished that. So the ln of 2, I'm going to write this out to more than 4 decimal places because I want to know when I've reached my goal here. So it is 0 point, I'm just going to put 0.6931471 8, and I'll probably just stop there. That's plenty. That's plenty. So Identify the limit x accurate to 4 decimal places. Accurate to 4 decimal places would be 0.6931. So that is the limit x accurate to 4 decimal places. That's that part. Okay. So that was kind of the point of doing all that, is to get that. I want to write it to more than 4 just so I know when I've reached my goal, and just for a little bit of a buffer. You don't necessarily have to do that, but I don't know. I'm just trying to be thorough. So the next thing I would do is go ahead and take the derivative, because the formula includes the derivative of f. So I'm going to rewrite f first. F of x is equal to e to the x minus 2. So its derivative is actually not that bad. It would just be e to the x. Derivative of e to the x is e to the x, and then derivative of any constant is 0. So it would just be that. So I noticed for 55, the answer key did not clean up the formula very much at all, like hardly at all. So you don't necessarily have to clean it up. I feel like this one is going to clean up pretty well, though, because of how similar the derivative is to the original. So if I write this as f of x sub n, I would just replace x with x sub n. That's all I'm doing. Minus 2 over e to the x sub n. That's actually it. So we could distribute a little here. That would be x sub n minus, and this would be minus, if we put the negative down here, let's say, then this would be e to the x sub n over negative e to the x sub n, which would just be minus 1. And then I would have negative 2 over negative e to the x sub n, so that's going to be plus, because the negatives cancel, 2 over e to the x sub n. So I do like to clean it up a little bit if it's not too much work, just because you're probably going to be plugging in. If you're not plugging in, if you're using a calculator or Desmos or something for the whole thing, then I guess you don't really need to clean it up that much. You're just going to type in the whole function into Desmos or into your graphing calculator. So if you're doing that, awesome. You don't have to clean it up. But if you're doing it by hand at any level, whether you're using a graphing calculator or a scientific calculator especially, then I would probably clean it up, because then it's just going to be less work to have to type that in every time than to type in the less simplified version. So it's going to be a little bit of work at the beginning, and the payoff is a lot less work overall, if that makes sense. So that's our recursive or quasi-recursive formula here. So blah, 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 write out the formula for x sub n. So we just did that. If the sequence appears to converge, give an exact formula for the solution x. Well, let's see if it converges. I didn't really need to see if it converges for number 55, so I didn't put a big emphasis on the t-chart for number 55, because I posted the answer in the problem itself, so we already knew that it did. So I wouldn't really call it cheating, but we had the answer right off the bat. So we didn't need to focus that much on it. Here we do, because we want to make sure it's working, and I think all of these work. The only time I would see it not working is if you had some sort of undefined, like if f of x is 0, then you would end up with like a vertical asymptote there or something. Then I think maybe it might not work as well then. But even then, maybe you'd have a one-sided limit of infinity or something. But maybe that probably wouldn't be considered to be convergent though. So let's see. So we're starting off with n equals 0, because x sub 0 they already gave us. X sub 0 is 1. Then n is 1. Okay, so then let's plug it into the formula, right? So it would be x sub 0. We're plugging in 0 for n, but what we're finding is x sub 1. Okay, so it seems a little weird, but that's how recursive formulas work, so just get used to it, I guess. We're plugging in 0 for n, but we're solving for x sub 1. Okay, so when n is 1, x sub 1 would be what? Is what we're doing here. So it'd be x sub 0 minus 1 plus 2 over e to the x sub 0. So what would that be? Well, we know x sub 0. We know x sub 0 is 1. So it'd be 1 minus 1, so that's 0, plus 2 over e to the 1 power. So that cancels, and then it would be 2 over e. So we would get exactly 2 over e, but we do also want to keep in mind what these decimal approximations are. So I'm actually just going to type in the function. Let's go ahead and find out what 2 over e is first. So let me go ahead and type that in. I'm going to keep my tab for, I have Desmos pulled up over here. That's what I'm looking at. I do have ln of 2 stuck there. I'm going to leave that in its own little column or row on Desmos, just so I have that written down. I already have it written down as well, but just to leave it there. So 2 over e is 0.7, so we're not even accurate to 1 decimal place yet. So I'll probably just write 0.7-ish, 0.7 dot dot dot, because we're still not quite there. The first decimal is 0.6. Now, granted, it's 0.69, which is really close to 0.7, but we're not even accurate to 1 decimal place yet. So we'll probably just leave that there. Now, for the rest of these, what I can do is I'm going to go ahead and write out f of x. So if you're doing this on Desmos and you want to follow along with me, here's what I'm doing. And actually, you know what? Let me go ahead and pull this over so you guys can see this. So it's going to be f of x equals e to the x minus 2. I already have the other one pulled up, but let me put this over here so you guys can see this. So I have this. This is the previous one that I was just doing. So I'm going to backspace it out here. So I'm going to write f of x equals, and then it's going to be just x. We had x, and then what was the rest of it? I wrote it over here. X minus 1 plus 2 over e to the x. Now, don't get too caught up on what this graph looks like. If you guys can see this graph, it's got a diagonal asymptote. This is not the explicit formula. This is the recursive formula. So we can't be like, oh, look, the limit is undefined. It doesn't converge. No. This is the recursive formula. I'm just writing it out as if it were an explicit formula. Okay, so don't get too hasty there. There's the 2 over e. This was from the previous problem as well. I'm going to cancel that out there. So what we're going to do is we're going to use the recursive, but we can use the recursive formula to find out what the next value is going to be, because what I'm going to do is I'm going to want f of, not 2, because that's an in value. What I want is, I want to find out what x sub 2 is. But in order to find out what x sub 2 is, I plug in 1 for n, which means I'm looking at I'm looking at the value x sub 1 for my x value. Well, x sub 1 is 2 over e. 2 over e is what I'm plugging in then, because that is x sub 1. If I plug in x sub 1, my x sub 1 value into my x for f of x, then I'm finding out what x sub 2 is. Okay, so hopefully that makes a little bit of sense at least. Now, this is going to be a little bit more accurate. This is the trick with this now is that before I could have maybe written it as a fraction when it was able to be written as a fraction. E is a transcendental number. It's a special kind of irrational number. So I cannot write this as a fraction. That's a little bit, I want to be careful with this because earlier I was just like, whatever, 0.7-ish. But now that I cannot, I don't know what this 0.694 blah, 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 blah. I don't know how to write that as a fraction because Desmos won't write it as a fraction because it can't write it as a rational number. So I can't do that. But what I can do is I can write out a bunch of decimal places, or I can just copy it. So actually on Desmos, I can copy this number, Control C, and then I can plug that number in next. Okay, but on the board, I'm going to go ahead and write this out. So 0.69, oh, because I was writing on the board, it got rid of this. I'm going to move this back over. I'm going to move this back over here, over on my monitor. So 2 over e is, and then it's 0.694, so 2 decimal places so far. 0.694 I'm going to put dot, 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 dot. We're going to just stop there because I have it written on Desmos. So 0.694. We're now accurate to 2 decimal places. We need to get to 4 decimal places before we can stop. So I already copied that 0.69 value. That value now gets plugged in, and I want f of that 0.694, blah, 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 that number. So I just copied it, and I'm going to paste it. If you can't do that, then on a graphing calculator, you just have to write down the value, write it out as many decimal places as you can, and then put that in, like f of that. So it takes it out to like 10 decimal places for me. It's 0.694042299919. So that's accurate enough, I think. So that is going to give us an n value of 3. And let's see. Oh, backspace. There we go. Okay. So an n value of 3. And what does that come out to be? It comes out to be a pretty accurate number. We're getting there. Actually, I think we might be there. Yeah, we got it. We're there. Because this is 0.6931475581. Oh, I was like writing while I wasn't looking. 7, that's a 5. So we're pretty accurate here. That's 169314771. So the correct is a 1. But that's 1, 2, 1, 2, 3, 4, 5, 6. That's 6 decimal places. So we're good. We only went to 2 decimal places of accuracy with n equals 2, but we're at 6 decimal places of accuracy with n equals 3. So the last part of this, if the sequence appears to converge, give an exact formula for the solution x. So you might write out something like the limit as n goes to infinity of x sub n is equal to, and then it would be equal to the ln of 2. So that's basically this. And then the smallest n, such that x sub n agrees with x up to 4 decimal places, the smallest n would be n equals 3. So that last answer, n equals 3, is accurate to 6 decimal places. And that's the smallest n such that x sub n agrees with it up to, or more than, of course, 4 decimal places. Because if it's accurate to 6, then it's also accurate to 4, right? So there we go. So yeah, these questions are so long. I feel like all of these take forever to do. And there's a few more of these, so we're getting there. We're almost there. Hopefully this has been helpful. Go check out the 5 math mistakes everyone makes and how to avoid them. It's a free PDF I have on my website, myersmathematics.com. Link down in the description below, and you can go check me out and see what I have on there. If you want to inquire about tutoring or just other resources that I have as a tutor and as a teacher and as a content creator. So go check it out, and I'll catch you guys in the next video. Blessings, y'all.